Okay, so now let's go and talk about the more realistic problem in classification, where you have non-separable clouds of points. So imagine this data set in which you have, for example, in this case, two outliers. So you have this point, this circle, this red circle. If this problem were linearly separable, this point would be at most in this position here. But in this case, it is in the other side of the decision boundary. This is the decision boundary, okay? And we can measure how far away is from this line that is like the line defined by the support vector. So this is a support vector, this is a support vector, and this is a third support vector. So this C distance, you can compute that for every point that is an outlier, or actually you compute that for every point. So of course, points that are well located before or below the support vector, they won't have any impact in the optimization of the problem, because here we are considering all those points that are outliers. So in this case, you see here this blue square, and you can compute the distance from the region of the support vector machine of its same class, which in this case are the blue squares. So what we are going to do is to consider these distances, and we are going to add more terms to our optimization problem. So if you remember, in the linearly separable case, our objective function was only this part here, 1/2 of the square of the norm of our parameter vector W. Now we are going to consider also the sum of all the distances of the outliers, this Ci, from I going from 1 to m. And we are going to give it some cost or some weight, which is doing this constant C. Okay, so if you notice here in this function, if you make C equals 0, then you're simply saying, I don't care about the outliers. And you will go back to the first optimization problem, and what you're going to do is simply ignore your outliers. So this C, you will also have time to experiment a bit with this. You need to find the best parameter C and for your data set. So this parameter depends on your data set. Okay, and well, now that we are considering these distances of the outliers, we need to also modify our constraints. So now we are going to allow our points to have functional margins less than 1. If you remember, in the first problem, the minimum margin allowed was 1. So this product here, we said it could be at least 1 or larger than 1. Now we are adding these distances of the outliers, and this means that the distance, the functional distance could be smaller than 1. And also we are going to say that our distances should be at least 0, these psi distances. So as I said, examples are now allowed to have functional margin less than 1. Therefore, when an example I has a functional margin 1 minus z, the cost of that solution will be increased by c times ci. The parameter c controls the relative weighting between the twin goals, which are making this large and ensuring that most examples have functional margin at least 1. Okay, so as we saw in the previous presentation, we need to build this Lagrangian function in which we put together our objective function and all of our constraint functions each of our constraint functions will be multiplied by some factor. So these two terms here are our objective function. Here we have our first set of constraints about the functional margin, and here is the last set of constraints where we are saying that this should be larger than 0, or at least 0. And here alphas and r's are the Lagrange multipliers, and this should be at least 0. So we proceed in the same way that we did it with the separable case. We need to compute the derivatives, the partial derivatives of this Lagrangian with respect to w and b. And when you do that, you get exactly with the same function that we got in the first problem. And the only difference is that now we have the c here that is going to bound the values of the alphas. In the previous problem, we didn't have c, and this constraint was simply that alpha could be at most at least 0 or larger than 0. And this constraint we had it also before. It was saying that the sum of these products for the m example should be 0. So mainly the only difference is that we have this upper bound for the values of the alphas. Now, and in the same way that in the previous problem we got to a w function that was a function of alphas, and this function is something that we wanted to maximize. Now we are going to see how we can maximize that using an algorithm. So first, maybe we can try to approach this problem of maximization by focusing at each time only on one alpha. Like for example, consider first working with alpha 1 and trying to maximize this function in the dimension of alpha I or alpha 1, and then you move to alpha 2, you give values to all the remaining alphas, and you optimize with respect of alpha 2. Then once you have done that, you go on and you optimize with respect of alpha 3 and so on. Well, that could be an approach that seems interesting, but there is a problem if you want to do that. The problem is that we have these constraints here. First, that we have this alpha that it is telling you this should be smaller than c. But at this point, the most important constraint are this one, in which we say if you sum the products of alphas and y's for every point in your data set, the result of that sum should be 0. So if you try to run this algorithm, the problem is that when you add or subtract something to alpha 1, for example, then at that moment you cannot be sure, you cannot guarantee that this constraint is going to be satisfied. So the problem is then that this way of saying, okay, I'm going to update, for example, alpha 1 and then alpha 2 and then again alpha 1, that is not going to work because of this constraint here. Okay, so we cannot optimize one parameter alpha at a time. Well, what we need to do is to optimize 2 alphas at a time. So from this expression, first see that you can move to the left the first term that will refer to alpha 1 times y1. Okay, and in the right side we will get this expression, which are the remaining m-1 products. Okay, and you can solve this for alpha 1, so we move also the y to the right side. So here you see an expression of alpha 1 in terms of the other alphas and y's. So the algorithm, which is called sequential minimal optimization, it consists in selecting pairs of alphas, alpha I and alpha j, and we optimize the function w with respect of these two parameters, okay, while holding all the others alpha k, where k are different to I and j, fixed. So the idea is that we assign some values to the other alphas, and we work only with alpha I and alpha j. Once we have optimized this function with respect to these parameters, we take other pair of alphas and do the same. So from this constraint, where this should be 0, we can also write this expression, just emphasizing the sum of the products for the two first alphas, alpha 1 and alpha 2. This will be equal to minus the sum of the remaining products. And by making this some constant, that here we are calling this constant some zeta, we see that this is basically an equation of a straight line. Okay, so if we make this some arbitrary constant, some number here, we give it here some number, then we can focus exclusively on alpha 1 and alpha 2. And that's what we are saying here is, let's say, okay, we don't care about this at this moment. We are going to focus only on alpha 1 and alpha 2. This is our first pair of parameters. And in the same way, you can solve this equation for alpha 1, and you will get this. Now, if we plot that equation for the straight line, here you can see alpha 1 times y1 plus alpha 2 y2 equals some zeta number. We have the equation of the straight line, and we can see here that this is a easy problem, because then we have only two parameters. We have a function of two parameters instead of having m parameters. We have only two, and here we see some boundaries, like for example to the right there is a constraint saying that alpha cannot be larger than z, which is the cost of the distances of the outliers. So you have also the same here, the same c value. So for any alpha that you assign, to get the alpha 2, you just need to evaluate the equation of the straight line that you are working with. Okay, and this square is telling you that the combination of alpha 1 and alpha 2 cannot go or be located outside this square because of the constraint imposed by c. And also we are saying here that for example, alpha 2 cannot be larger than h, because h is the last value that can be part of the straight line and also be inside the square. So this is like the highest value that could be assigned to alpha 2, and here would be the lowest value assigned that could be assigned to alpha 2. So suppose that this straight line passes in this side over here, we will have some minimum L in this position. Okay, so what we do then is to rewrite the function of the alphas, replacing alpha 1 by the expression that we computed before, this one here. Instead of writing alpha 1, we are going to write this product, and treating alpha 3 to alpha m as constants, we get a quadratic function that can be easily maximized by setting its derivative to 0 and solving for alpha 2. So when we say, okay, let's give some random numbers to this here initially, and let's start updating alpha 1 and alpha 2, this function will be a quadratic function. You just need to compute the derivative of that with respect to alpha 2 or alpha 1, and then solve to get the values, the next values for alpha 1 and alpha 2. Then what you do is take another pair of alphas and do the same. So as we said in the plot before, if alpha 2 is larger than h, when you solve this, you need to bound it. So you will give it at most the value of h. This is to be sure that alpha 2 is going to hold this equality true. And remember that this equality true is making sure that the sum of all the products alpha and y are going to be 0. So if alpha 2 in this process, alpha 2 is larger than h, you force the value of alpha 2 to be h, at most h, and if it is lower than L, you need to force alpha 2 to take the value L. Finally, having found alpha 2, we can calculate alpha 1 from the expression that we got before. Okay, once you have alpha 2, you can compute what is your alpha 1. Okay, so this is mainly the algorithm that we use for solving this optimization problem. In this last part, when we need to maximize this, which is a function of the alphas. So as we said, we need to take pairs of alphas and give some constant values to the other alphas and repeat this algorithm. So this algorithm is the standard algorithm for solving or programming support vector machines. This is the algorithm that is already implemented in this library, which is by far the most well known and applied library. The name is lib SVM. And there are versions of this that you can use or call from MATLAB or from C++, and also it is included in the, I think it is included in the scikit-learn library in Python. So in the exercise on support vector machines, you will have time to play with this library and run some experiments. Okay, so this was the last presentation of support vector machines. I hope this is useful. I thank you guys and talk to you later. Bye.